Hello, today we will talk about clouds and their observation from space. Clouds play a crucial role in Earth's energy balance and climate system, but our understanding of their impact is still limited by a number of uncertainties. To improve our knowledge about clouds, scientists rely on satellite observations, particularly those obtained from lidar instruments because they provide detailed information about clouds. By the way, what is a lidar? We need to say a few words about this instrument. By emitting laser light and analyzing the backscattered signals, atmospheric lidar can provide valuable information about atmospheric composition and structure. The time it takes for the laser light to travel to a certain height and back helps to calculate the exact height of the probed area, and the backscatter signal at this height contains the information about atmospheric molecules and particles. However, comparing cloud data from different lidar instruments is challenging due to numerous differences between these instruments. Have a look. The pictures on the left and right show the orbits and cloud observations by two space-borne lidars, Calliope aboard Calypso and Aladdin onboard Aeolus satellites respectively. As one can see, the observations do not happen at the same local time. Note the Earth's rotation and 4.5-hour difference between A and B panels. The observation viewing angles are different, check the green and violet lines, and the wavelengths are different too. Additionally, the Aladdin instrument does not measure the cross-polar component of backscattered radiance, which further complicates the comparison, and this is not the last difference. In a recent study funded by European Space Agency ESA, the researchers from the Laboratory of Dynamic Meteorology, LMD, at Sorbonne University in Paris, France, proposed a method to merge cloud data from these two lidars. One challenge addressed in the study was the inability of Aladdin to measure a specific component of backscattered light that is important for the analysis. To compensate for this limitation, the researchers developed a correction method using Calliope data. They analyzed the depolarized component of the light scattered by atmospheric particles as measured by Calliope and applied this information to fill in the missing data in Aladdin. Examples of this correction are shown on the slide. As one can see, in some cases, up to 50% of the radiance is missing. Another problem was the wavelength difference for these two lidars. This slide illustrates the problem using the simultaneous measurements of the atmosphere by a pair of nasal arc leaders at two wavelengths. The upper and lower panels represent so-called lidar curtains, which are composed of a set of vertical profiles gathered while the lidars were moving and measuring the backscatter over the same scene. As one can see, the images resemble each other, but they are not identical because the light scattering by atmospheric molecules at 355 nanometers, the wavelength of Aladdin, is stronger than that at 532 nanometers, the wavelength used by Calliope. So the researchers had to develop the wavelength conversion method for the backscattered signal to compare apples to apples and to define the clouds the same way for both satellites. Then the researchers took into account the diurnal cycle, that is the cloud fraction variation throughout the day. Since Aeolus and Calypso overpass a given area at different local solar times, the adjustments were made using the observations from the other instruments, CATS lidar, on the top, or a combination AIRS and ISE infrared sounders in the bottom, to determine the diurnal cycle of clouds and correct the Aladdin data accordingly. As one can see on this slide, the difference in cloud fraction due to the diurnal cycle might be up to 30% for some cloud types. The researchers proposed a solution to fix this discrepancy too. After applying all the corrections and adjustments, the researchers managed to make the Aladdin clouds similar to Calliope clouds. On these slides, we can see how the step-by-step correction improves the agreement of cloud fraction in latitudes and heights. All steps are important: the wavelength conversion, the depolarization, and the diurnal cycle. Finally, the researchers managed to merge the cloud data from Aladdin and Calliope. The cloud amount time series shown in this slide demonstrates a reasonable agreement between the two instruments. The mean difference of the global cloud amount is within a couple of percent. Curiously, both satellites will be deorbited at approximately the same time this year, but if Aeolus remained operational, the proposed technology would have helped to continue the series of cloud observations without compromising the quality. This study contributes to the development of a comprehensive global cloud record by enabling the integration of cloud data from different lidar instruments. This approach can be extended to include future lidar instruments like at LID onboard EarthCare, which will fly next year, facilitating a better understanding of clouds and their role in Earth's climate system.